Hello AP Statistics students. In this video we are continuing our look at probability and specifically we are going to look at some of the basic probability rules. Alright, so our objective here is we will apply basic probability rules to find the probability of certain events occurring. And we got to talk about what the heck an event is. We'll get there. So first off, what is a probability model? All right, so that's a specific thing in stats and probability theory. So a probability model is a description of a random process. All right, it has two things here for us. It includes all possible outcomes of this random process and the probability that each outcome could occur. All right, the first example will clear all that up. Another quick vocabulary is all those possible outcomes. We call that a sample space. All right, those might be a little familiar to you. If not, this example will clear up what those are. So here's our example. Imagine rolling 2 dice. What would the probability model look like? All right, so first you would have to list all possible outcomes. That is called the sample space. So here's a nice picture of that sample space. Don't worry, you usually don't have to do that. Please don't try to write all those dice down. But as you can see, they have all possible options, from getting a 1 and a 1, the snake eyes, to getting a double 6s. Isn't that straight to jail, do not pass, go? It's only if you get 3 times in a row, isn't it? Yeah. But all possible combinations of dice rolls are there between those 2 dice. So that's the first part you need for a probability model, listing out the sample space. The next is telling me the probability for each one. So a dice roll is completely random. If you count it up, this is a 6x6 rectangle here. There are 36 combinations. And so each one has a probability of 1 out of 36. So there is our probability model right there. All right, next, now that you have your probability model, what do you do with it? You can start defining events. So an event is any collection of outcomes from some random process. So each one of these individual options is an outcome. An outcome in our probability model. So here is my event now. So an event is any collection of outcomes. So we're going to define event A as rolling 2 dice and getting a sum of 5. All right, so we're going to take a look at what is the probability of getting a sum of 5. And we do usually give those names. This is event A, so this would be the probability of A occurring. Well, we got to do some probability then. What possible outcomes give me a sum of 5? Well, we could roll a 1 and then a 4. We could do a 4 and then a 1. Or we could do a 2 and a 3. Or a 3, then a 2. So those are the only ways that we can make a sum of 5. So how many options there? We got 8 options there. There's 8 ways to make a sum of 5. There are a total of 36 possible combinations in our sample space. So our probability is 8 out of 36, which is 1 over 4. So our probability here is 0.25. There is a 25% chance of getting a sum that equals 5. So remember, our event there was this idea that we are getting a sum of 5. All right, let's try another one of those. Here's a nice easy example. Maybe pause the video, try this one out on your own. I'll give you 2 seconds here, and then I will start working it out. All right, hopefully you got that, or if you're just here along for the ride, let's go. So give a probability model for this random process. So again, a probability model has 2 things. First, the sample space. So what are our possible options here? When we do this spinner, we could get, now here you want to sort of be careful about how you do the sample space, otherwise you might miss some. You want sort of a system. So I'm going to do all the reds first. I could get red, red. I could go red, blue. I could go red, yellow. All right, now I'm going to do all the blues. I could go blue, blue. I could go blue, yellow. Or I could go blue, red. Now the yellows, I could go yellow, yellow. I could go yellow, blue. Or I could go yellow, red. All right, there is my sample space. What is that? A total of 9 possibilities. So the next is the probability of any given outcome. The probability of any outcome is going to be equal to 1/9. There's 9 of them. They're all equally likely. The areas here are all the same. No quadrant, or what's a quadrant when it's only 3? Trident. Each one is equally in terms of equal in area, so I would assume it's an equal outcome or equal probability for each outcome there. So 1/9. All right, define event A as spinning a blue at least once. Find the probability of A. So the probability of A is equal to the probability of at least 1 blue, which is equal to, all right, how many have blues? 1, 2, 3, 4, and 5. So the probability there is 5/9. All right, those are our probability models a little bit. Let's springboard off of that. So some basic rules here. We've talked about this one here. I believe probability is always between 0 and 1. In our probability models, the total probability has to equal 1. Something has to happen, okay? If you take all the outcomes and you didn't miss any of them, they all have to add up to a total probability of 1. I can't come up here and spin my spinner and have it not land on a red, blue, or yellow. It's got to land somewhere unless I really just smack it off the table. But we're not talking about that right now, okay? So the probabilities all together have to equal 1. That's kind of a big thing. Next, the complement rule. This is the probability that something will not occur. What is the probability something will not occur? It is 1 minus the probability that it will. Okay, so if I want to know what the probability of no blues being spun, that will be 1 minus the probability of a blue being spun at some point. So in this case, the complement would be 1 minus 5/9, which is equal to 4/9. Sometimes that is easier than going back to your sample space and just circling all the ones that don't have a blue. 1, 2, 3, 4. Especially if you've already done the probability. But little syntax here for you. The way we write that, okay? There's a special way of writing complement. So didn't we name that one? Wasn't it A? Yeah, so this is event A, right? The complement of that would be written the probability of A and then a C at the top for complement, okay? So that is the same as the probability of not A. which is equal to 1 minus the probability of A. So that's just a little syntax you want to remember if you see that little power of C. That is a complement. That is the probability of it not happening. So what is the probability of rolling 2 dice and the sum is not 5? All right, so we could write that as the probability of not a sum of 5. That would be the probability of the sum of 5 complement, which is equal to 1 minus the probability of a sum of 5. Now, of course, you don't have to do all of these, right? These are all the same, just showing you different ways of thinking about it. They are all the same, though. It's all going to be 1 minus, wasn't it 25%? I forget now. Yeah, 25%. There it is. So 1 minus 0.25, which is 0.75. That's the complement rule. All right, next rule here. Mutually exclusive addition rule. Holy crap, Bolt, that escalated quickly, didn't it? I was with you with the complement, and now what is this? All right, so it's not that bad. It's not that bad. So the mutually exclusive addition rule means you are allowed to add probabilities together as long as the events are mutually exclusive. All right, Bolt, what the heck does that mean? That means the outcomes do not overlap. The outcomes do not overlap. Okay, so take one dice roll. All right, imagine one dice roll. We could roll either a 1, a 2, a 3, a 4, a 5, or a 6. And for each one of those, we have a 1/6 chance, right? It's a dice roll. 1/6, 1/6, 1/6. All right, so what if I now wanted to know what is the probability of getting either a 1 or a 2? So, do those two outcomes overlap? If I only roll one dice, is it possible to roll a 1 and a 2 at the same time? Obviously not. They cannot happen at the same time. It would be impossible to have a 1 and a 2 show up on the same dice roll. They are mutually exclusive. So, the addition rule says I'm allowed to take the probability of the first one plus the probability of the second one. And so in this case, it would be 1/6 plus 1/6, which is equal to 2/6, which is equal to 1/3. All right. So put completely algebraically, the probability of A or B is equal to the probability of A plus the probability of B. So that is the mutually exclusive addition rule. And it only works if event A and B have no overlap. All right, they can't happen at the same time, just like you cannot roll a 1 and a 2 and a 3, 4, no, sorry. You cannot roll a 1 and a 2 at the same time. They are mutually exclusive. That is a big word. That is a word you want it to understand and know. All right, quick example of that. Avoiding blue M&Ms. So suppose you tear open the corner of a bag of M&Ms. You probably have a few of those lying around, right? After Halloween, pour one candy into your hand and observe the color. According to Mars Incorporated, the maker of M&Ms, the probability model for a bag from its Cleveland factory is blank. Okay? Blue, orange, green, yellow, red, and brown are our color options. Explain why this is a valid probability model. All right, so what do they mean there? Is it valid? So first, each outcome has a probability less than 1. I guess between 0 and 1. Between 0 and 1. All right. You can't have a probability greater than 1. Nothing can happen more than 100% of the time. And the other thing that has to be true about a probability model, all of them together have to equal 1. All right. So if you add all of those together, the sum of all outcome probabilities equals 1. And if you want to check me, go ahead, add all those numbers up. They do, in fact, equal 1. All right, part B. Find the probability that you don't get a blue M&M. Hey, so this is the probability of blue complement. So I could add up all the not blues. I could add up this one, plus this one, plus this one, plus this one, plus this one. Or I could use the complement rule and do 1 minus this one. Whichever is easier in your eyes to do. I'm going to use the complement rule. This will equal 1 minus the probability of blue. So that will be 1 minus 0.207, which is equal to 0.793, I believe, is our probability there. All right, and the one that we're really looking forward to here with this example is part C. What is the probability of getting an orange or a brown? The probability of an orange or a brown. Now, can I use the addition rule? Are those mutually exclusive? Well, I can't. If I pick one M&M out, it can't be both orange and brown. There's no overlap between brown and orange. So they are mutually exclusive. I'm allowed to use the addition rule. So that will be probability of orange plus the probability of brown. So that will equal 0.205 plus 0.124, which is equal to 0.329. So one more idea there of mutually exclusive. When you pick an M&M out of the bag, it has to be one color. It cannot be two colors at once because the colors are mutually exclusive. Okay, nice and simple there. And sadly, you can only use the simple rule for a mutually exclusive event. So what happens when they are not mutually exclusive? So here is an example where we have some events that are not mutually exclusive. So students in a college stats class wanted to find out how common it is for young adults to have their ears pierced. They recorded data on 2 variables, gender and whether or not the student had a pierced ear, for all 178 people in the class. The two-way table summarizes the data. All right, so we've been pretty familiar with two-way tables and how to do probability, so a lot of this should be sort of a review. So A, find the probability of event B. All right, event B is getting a student with a pierced ear, and event A is a male student. So picking a male student is event A. So we first just want the probability of B. What is the probability of getting a student with a pierced ear? So we just head over to our two-way table. Pierced ear, yes, that is a total of 103 people out of the entire total of 178. So that is 103 over 178. Whatever decimal that gives you, the decimal is not exactly that important, but just so you see, it's 103 over 178. Part B. We'll find the probability of A and B. So what is the probability of being A male student, and B, having a pierced ear? Well, we've used two-way tables before. We know that we just go to the table and find the cell that matches that. A male pierced ear is 19. Our total is the total of 178. So that will be 19 over 178. And part C, here is where we're looking at a modified addition rule. What is the probability of A or B? So a male or pierced ear. All right, so who are we talking about? Who fits the description of a male or pierced ear? All right, let me grab the highlighter here. Who fits that description? All right, so male, so these people do. All right, pierced ear, well, that's this horizontal column right here. So these people in green all fit the description, a male or a pierced ear. Okay, this is like, so it's an inclusive or, in that you can have one, you can have the other, or you can be both. You can be a male, you can have a pierced ear, or you can be both. Okay, so if we add all of those up, we get 71 plus 19 plus 84. Those are the people we're talking about, over the total of 178. That doesn't look a whole lot like the addition rule there, does it? That is not, I'm going to put a big slash through this equal sign. That is not the probability of being a male plus the probability of having a pierced ear. A plus B. That is not the same. Okay, that is not equal to, put another big slash, the probability of A, which is, A is a male student, 90 out of 178, plus the probability of B, which is 103 out of 178. Those are not the same. Okay? If I take a look at those totals here, if I take 71 plus 19 plus 84, I get 174 out of 178. 71 plus 19 plus 84. Yeah, because there's only 4 people that it didn't cover, right? 174 out of 178. But this one over here is 193 out of 178. Well, that's wrong for so many reasons. You can't have a probability bigger than 1. The addition rule didn't work. Why? Because if I do 90 plus 103, let's take a color here. If I do 90, that's these people. And I take 103, that's these people. Do you see which number I'm double counting when I do that? I'm double counting the 19. Because these weren't mutually exclusive, if you do that simple addition rule, you double count one of the parts of your two-way table. You can't do that. So how do we fix it so there actually is an addition rule? Well, because you double counted one, you have to subtract it off. So if A and B are any two events resulting from some random process, the general addition rule says the probability of A or B is equal to, take a look at the simple one, probability of A plus the probability of B. But then you have to subtract off that piece that you double counted, the probability of A and B. And then that fixes your addition rule. And I can do that up here with the 193 if I subtract off the 19, because I double counted it. 193 minus 119 fixes it to 174 and makes it right again. Okay, that's the general addition rule. So now that we know that, we don't need the two-way table anymore. Okay, so here is one last example to leave you with about using that general addition rule without the two-way table. A survey of all residents in a large apartment complex reveals that 68% use Facebook, 28% use Instagram, and 25% do both. Oh, look at these old teachers trying to be with it and hip, trying to connect with the youngers. Look, we know about social media. Suppose we select a resident at random. What's the probability that the person uses Facebook or uses Instagram? So they could use Facebook, they could use Instagram, or they could use both. All right, that's the general addition rule because there's definitely overlap between Facebook and Instagram. They are not mutually exclusive. Some people use both. So here's how they use the general addition rule. They take the probability of Facebook, which they gave us, 68%. The probability of Instagram, which they gave us, is 28%. But remember that double counts the people that use both. So we have to subtract off one of those double counts, the probability of Facebook and Instagram, which is 25%. And we get the people that use one or the other or both is 71%. I hope that makes some sense, ladies and gentlemen. A few probability rules for you.